Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My pleasure to introduce Chen Ding. Chen's a professor at the University of Rochester. He got his PhD from Rice with Ken Kennedy. And so Chen has done a lot of work on compiler optimization, locality analysis, space analysis. He's been pretty active in helping organize workshop on memory system performance. And so we've been a big support of that. And so he's going to talk about behavior-based program analysis.
Okay. I first came to Microsoft before going to Rice for PhD, and the recruiter at Microsoft called me and invited me to interview at the MFC group. And that's 11 years ago. Time flies. Which is fine if it's not for the white hair that comes with it. And I know Ben and Tricia in last century. We remember 1998 ACE Plus conference in Boston, and I asked Keith Cooper, so who's the program chair for next year's PODI? And Keith told me to look for someone with a baby face.
Baby.
That's how I found the band. It was considered a remarkable success in 1999, only because I had a paper in Ben's conference. And when I came to the conference, Tricia had 2 papers in the same conference, and the first 2 papers, which are still the most influential for locality optimization for non-scientific applications. So it's very nice to be here and tell you about my work and learn more about research here. And there's no Rochester graduate here, so let me give you the quick summary about University of Rochester, which is a private institution. 5 years ago celebrated its sesquicentennial. And the campus, before I left, is in full bloom. Computer science was established as a PhD-only department in 1974, and in 30 years we graduated 147 PhD students, and recently added undergrad and master degree programs. And we have 13 faculty members specializing in artificial intelligence, computer systems, and computational theory. AI is the strongest of the 3. In this small department, we have 3 triple AI fellows. And my senior colleagues are known for field-shaping research in computer vision, artificial intelligence, natural language processing. The system research has an interesting history at Rochester. In mid-70s, everybody was using mainframe IBM computers logging in from terminals, except in Xerox PARC. We have workstations. And Xerox was headquartered at Rochester. So my department was the only place outside Xerox PARC that has the Xerox workstation, personal workstations, graphical user interface, mouses, and Ethernet in 1970. In 1980s, the department's 128-node BBM Butterfly processor is the largest shared memory multiprocessor, not just anywhere in the university, but anywhere in the world. And the research with Butterfly have influenced the whole generation of parallel operating systems and applications. And our graduates have gone outstanding careers, and the Rick Rashid and Galen Hunt are examples working in industry. And a little over a third of our graduates went to universities. At least 24 are now holding senior faculty positions, and 39 more recent graduates are holding junior positions, and soon to join them is my first student, Hita, who will start at George Mason in August. And she was an intern here, working for Tricia. And the system group spans OCS and the ECE departments, and there are 6 people. I'm putting the rest of the group on this slide. Michael Scott is the most senior. He's the Gallant's advisor. His work, along with your alum, John Milacrami, served to launch the field of scalable synchronization. And he's also the author of a popular textbook, Programming Language Pragmatics, that's currently being used in over 100 universities and colleges. And Sandia Dulkadis came from the trademark group at Rice, and she, over the years, has branched into many different areas. In the past 2 years, her papers appeared in ISCA, SIGCOMM, SIGMetrics, and SIGIR. And Kai Shang was a child prodigy. He was the gold medalist for this International Mathematics Olympiad. Wendy Hanselman came to us from MIT working on sensor networks after she declined the faculty position offer from MIT. And Michael Huang has been pioneering work in self-tuning processors and program phase analysis. Right? I'm sort of a black sheep, a flying fish, depending on the level you look at in this group, because everybody else is talking about building a system to run applications better. I'm looking at, as the rest of you do, looking at how to change the programs to use the system better. And the problem, not surprisingly, is this little nagging thing that there's a difference between how program looks and what it does. And at the undergraduate level, we teach programs consist of statements, procedures, variables, data structures. And then when they move to higher level courses, we teach them that there are data and control flows, and there are types. And also, if you want to reorganize a program, you need to understand dependencies. But that's the static view. It has a lot of structures. At runtime, however, a sequential program, when it runs, is just a sequence, a long sequence of operations. I emphasize the word long here because modern processors are capable of executing upward 1 billion operations a second. And there is no structure. All the static structures disappeared when we look at the runtime behavior. And also this trace, the execution trace changes when the program takes in a different input. So this is what I call behavior. It's really the operations of the program and the order in which the operations happen. Our best success for behavior optimization is actually dependence theory and loopness optimization. There we understand the structure of the computation, the structure of data, and we can solve equations to really optimize the behavior, such as blocking and loop fusion. However, that can go only as far as the appearance matches with the substance. The computation structure is the program structure. In increasing number of programs, and also when we look at the larger systems, it's not the case because we use abstractions, components, dynamic data allocation, late binding, and it's often not clear by looking at the program code, the behavior is often not clear. So that led us to look at the notions of locality and phases as a way to characterize structures in dynamic behavior. And it's an open question whether these concepts can be as useful as loops and data structures for programmers. And as academic, I also care about whether we can develop as rigorous theory we have for dependencies and types. And the approach we take is what I call behavior-based program analysis. So we first take a few inputs and do behavior profiling. But here is the departure from previous profiling techniques. We build a model. We try to capture not just the behavior of the few training runs, but also the behavior across all other inputs. And once we have this model, we go back to the program to link the behavior with the program code. And then, very importantly, we need to verify. And then we can use this model for improving program performance. And I'll talk about three models. The first is a quantitative definition of whole program locality. And then I'll subdivide the whole program behavior in space and in time and talk about reference affinity and program phases. And program models are not new. In 1976, Alan Smith noted that two different and plausible mathematical models of program behavior have yielded exactly opposite predictions. So at least bad programming models are not new. And in 1980, Peter Denning said politely that a program model should be built from real data. And just recently, he published a paper in Communication of ACM talking about something I care very much about, which is whether computer science is science. He gave a very positive answer and a positive outlook, including a hope that we may one day develop a theory of locality. So I'll put this up. What I'm trying to say is that we need to make sure that the models we develop matches with the locality, with reality, and also when we fail, we need to keep trying. So next, I'm going to build the first model from real data. Given a trace, I define reuse distance for every access as the number of distinct data elements between this and the previous access to the same data. And it was first defined by Mattis and others in 1970 in the paper IBM System Journal. And then once I get the reuse distance for all accesses in a trace, I get the distribution of these distances, which I call reuse signature. So take these 7 accesses. If I look at the last access, and I can see that the reuse distance is 2 because there are A and C access between the first access B and the second access B. To get the reuse signature, I calculate the reuse distance for all elements in the trace, and then take the histogram. I drop the first access to each data element, and also I use relative percentage references at the y-axis. So what this signature says, there are 50% of reuses have a reuse distance of 2. And reuse signature is a good metric for locality because it's bounded. So just because a program runs forever doesn't mean it has infinite locality. And also, it's purely the property of a trace. It's hardware independent. In addition to that, it's a good measure of the runtime behavior. The coding styles that sort of change the appearance but doesn't change the behavior, such as loop unrolling and allocating variables in different locations, none of this actually changes the reuse signature. So this is a metric that's relatively insensitive to the coding styles of the program. Efficiency is a problem in reuse distance measurement. A naive algorithm would take O(n) square in time and O(n) in space, where n is the length of the trace. And we use m to denote the size of data accessed by a trace. In our experiments, n is up to 120 billion, and m is to 100 millions. over the past 30 years, a number of clever algorithms are developed for calculating reuse distance. Before 2003, the state of art was to organize the trees as a search tree. And then the reuse distance measurement is basically a tree search through this tree and back up. So the space cost is proportional to the size of program data, and time cost is n log m. For each element of the trace, we need to do a tree search. And it's slow mainly because of long distance reuses. But in that case, we often don't care the exact number. If the reuse distance is 1 million, we often don't, it rarely matters whether it's 1 million or 1,000,001. So what I figured out is that if we use approximation, if we just get the first few digits right, then we can reduce the asymptotic complexity, the space complexity from m to log m. And then the tree search on a tree of this size becomes log m. And for all practical size of trees, it's near to the size of the trees. So I want to show you the effect of approximation on one example analysis for FFT. In this particular input, it has about 66,000 distinct data elements. And then the accurate measurement will have the same number of tree nodes. And I'm giving you only the upper part of the reuse signature, starting from 55,000 to 66,000 in a series of linear sized bins. If we want to be more efficient, with 1/10 of the tree size, we get 99.9% accuracy, and there is no visible difference between the two. And to be really efficient with 800 tree nodes, we can get 99% accuracy, and very close match to the accurate reuse signature. And what the algorithm actually can guarantee the accuracy. So if it's 99%, that means the measured reuse distance is guaranteed to be between 99% and 100% of the actual distance. So this picture is for show only, and we have the proof that it's accurate. But then the efficiency allows us to measure reuse signature for real applications on real size inputs. And then we build a model to try to capture the common patterns in the reuse signature. So given a program, we take a bunch of training runs and get their reuse signatures. Then we divide the references into groups based on their length. For each length group, we identify how the reuse distance change from one input to another. It may not change, then we say it's constant pattern. And it may change linearly to the size of program data, or it change in sublinear fashions. Then we can do regression analysis to find the parameters for these changing patterns. We can solve a small number or large number of equations based on the accuracy that the user wants. After that, I'll have a model that's supposed to tell me the reuse signature, not just for the few training rounds, but all other runs as well. And this parameter it's captured by this algorithm we call distance-based sampling, and is sort of finding a representative reuse distance. And for all programs except one, it's proportional to the size of program data. So for practical purpose, just view the parameter as the size of program data. But if we want to predict the reuse signature before running a program, then we use the sampling at the beginning of the execution to get this parameter. And then we verify them. So here is a scientific benchmark from Spec 2000 that's testing the primality of large numbers, really large numbers, that's 2 to the thousands of power. So in behavior-based program analysis, we take 2 training runs, get their reuse signature, and then we build a model. that's supposed to tell us the re-signature for all other runs. And just look at these two training runs, we see that part of the reuses do not change their distance, and part of the reuses change the distance. So then we do regression analysis. In this case, it's really extrapolation. And then we have the model. We use distance-based sampling to get the required parameter and plug into the model. Then we have this prediction that the reuse signature for the new input, the reference input, is going to be this. The first part looks fine, but this part seems fictitious. The distance, reuse distance, is a factor of 10,000, 1,000 larger than the reuse distance here. But the more radical prediction is, the more suspense we have when waiting for the confirmation. So if we wait for this reference run to finish after 644 billion memory accesses, the verdict comes. The predicted reuse signature and the actual reuse signature overlap by over 95%. Two signatures match. And the model is able to predict execution that's 10,000 times longer than the ones used in the training run.
So in this model, is the number of accesses also a parameter?
Percentages. So, right, the model cannot predict the length of the execution, but it will say, let's say, about 12% of all the references will have this list. Yeah.
So is GCC one of the 13 spec programs?
Yes. There are 17 programs total. Half are integer programs, half are floating point programs. And GCC we thought is too complex and demanding to be predictable, because GCC is sort of an input-dependent behavior. It compiles the functions in whatever file that user gives it. And so we tried GCC and it turned out to be an anti-climax. Vital picked out the shortest, the longest, and the 3 random inputs to the GCC from the spec benchmark set. And their reuse signatures overlap by, on average, 98%. And the prediction is trivial here. We don't even need to do sampling. We can predict the reuse signature without running the program for a new input. So the interesting question is not how to predict, it's why this is predictable. And it's a combination of the inherent pattern in the compiler, GCC, and also part of the other factor is the input. So when we write functions, when we write C functions, we don't write functions of arbitrary length. Sort of the length distribution of these functions that programmers write follows a fairly steady distribution. And so that's part of the reason why we see this constant pattern. We also tried inputs that have functions with thousands of lines of code, and still the overlap was over 80%. So there are really 2 factors. One is the compiler, the other is the input. And from that, we can have a quantitative definition of whole program locality, which is the miss rate across all data inputs and all cache sizes. So that's really precise definition of the locality. Then we can use that to evaluate compiler optimization. So I did loop fusion studies before to evaluate the improvement. I pick one input and run on one machine. So it's really comparing 2 points between these 2 plots. With the whole program locality model, I can see how the entire landscape changes by a program transformation. So it's behavior-based analysis. I'm not predicting this locality from the original program. It's just the I take the fused program and do behavior-based analysis and get a model. And see the effect of the transformation on whole program locality.
What are the axes here?
X is the size of cache. The x-axis is the size of the cache. The y-axis is the size of the input, so as measured by the number of cache blocks touched by the execution. And then the y-axis is the miss rate.
The z-axis.
The z-axis.
So is it the case that programs like GCC work well with this model because the complexity is kind of in the control flow and the static structure and not so much in the dynamic data access part of it? Is that kind of the takeaway?
GCC, when it compiles a function, it allocates dynamic structures to represent the parse tree or the control flow graph. We don't have the quantitative measure which portion of access is to heap data, to stack data, but I would imagine a lot of the memory accesses are to the heap. And the reason it has predictable pattern or constant pattern is that the length of the functions often have similar size, or the length distribution is constant. Then traversing these data structures, the reuse distance distribution is also constant.
So are there any programs where this thing didn't work very well at all? And what's the worst case?
The Lisp interpreter is our worst case in the published studies. There, the moving pattern is just not predictable because it's an interpreter based on what program is executing. The behavior can be very different. So for Lisp, we predict only the constant pattern. That's 70%. That's the lowest.
So the Lisp interpreter, this is a spec benchmark, right?
Right.
Lisp or whatever. So I think it has a garbage collector kind of as part of it. So that can be complicating things too.
Right. Yeah. But this one program, GZIP, is recently studied by undergrad in a class project. It has 3 different reuse signatures. It's not a single constant reuse signature. It's not a random reuse signature, but it has 3 distinct reuse signatures. When we give an input, it's either one of the 3. So that's another example. We're still continuing this study. But overall, really, what surprised us is that a surprisingly large number of programs, we see that they have different programs have different reuse signatures. And for the same program, the reuse signature seems to either consistent or if it changes in a consistent pattern. And this is what I call emergent behavior. It's nothing logical about this. There is no guarantee that complex programs have a consistent pattern. But through this observation, that's what we see, that's what we saw. But this is only a summary on average of the overall behavior. It's not complete. And 94% accuracy means is better than 90% accuracy, but still we may be missing billions of memory accesses in the long execution trace. And also, this doesn't give us the structure yet. And also, another point about GCC, when we look at the temporal behavior, which I will show a picture, is actually highly unpredictable. But the average seems predictable. This is giving the average. Just as if I ask you to give me numbers between 0 and 10, I cannot predict the next number you're going to give to me, but I can predict the average of all the numbers is going to be 5. Wait. Then our work look into final patterns to look at the spatial dimension and look at the locality relations among individual program data. So I'm next going to talk about the reference affinity. The name was coined by Ken Kennedy. And this is what I believe the most fundamental of the three models we have. And also this one has the most uses so far. A little bit of motivation. Spatial locality is important. And we say spatial locality depends on data layout. And then we measure the quality of data layout based on spatial locality. A more fundamental concept is what I call reference affinity. We want to place data that are accessed together into the same cache block, into the same memory page. And that's this relation of data is what I call reference affinity. A group of data have reference affinity if they're always accessed together in close distance. So we gave a very precise definition of what we mean by reference affinity. First, the rigorous notion of closeness is given by the linked path and the linked length. So given the trace, we say there are two axes are closely linked. And for example, in this trace, I give a subscript to mark different axes to the same data element. Then if I look at the W sub 1 and the Y sub 1, I see that they're linked by X sub 2 in the sense that I can go from W sub 1 to Y sub 1 in 2 hops, going through X sub 2. And the reuse distance of each hop is bounded by, is at most 2. And so we say there is 2 linked paths from W sub 1 to Y sub 1. And I have animation to say exactly the same thing. And now I extended the definition of reuse distance to be between accesses to different data elements. In fact, here is a requirement. Every hop, it must land on a different data element. And once I have this notion of closeness, I can define strict affinity group. We say a group of data elements G that have strict reference affinity group if and only if for any element in G and for any access to this element on the trace, it has a linked path to access to all other elements in the group. And it's a complex definition. And to make it more complex, we say the group has to be the largest possible. And then you may ask me, why do I want this complex definition that I cannot explain clearly with a few slides? The reason is that we want to guarantee certain properties, in particular the transitivity of the reference affinity relation, in that if A and B belongs to the same reference affinity group and B and C belongs to the same reference affinity group, I want to make sure that by my definition, A and C must belong to the same group. So I don't have the case where I want to group A and B into the same cache block and the B and the C into the same cache block, but not A and C. So I don't want that ambiguity. And then based on this parameter K, which is the bound on the reuse distance of the hop, each hop on the link of the link length, by changing this K, we can have a hierarchical structure of the program data. So now we have this a structure, at least by definition, have a structure of program data. So let's see an example trace. The top of this hierarchy is when K is infinite. Then any element has a linked path to any other element in the trace. So all the elements in the program in the trace belongs to the same affinity group. And then if I reduce k to 3, we see that W, X, Y, Z have closer reference affinity than they are with U and V. And a smaller k show their substructure within the group of W, X, Y, and Z. And the bottom of the hierarchy is when every data element belongs to its own group. And here, so this work is also sort of motivated by the Hofstream work by Tricia and trying to extend that notion. In the group notion, we allow these accesses to be in different orders with different frequencies. And of course, the other effect, the downside is that we cannot really do sort of prefetching improvement that Hofstream gave us. Really, here we try to capture large-scale patterns. When tens of thousands of elements that are often accessed together. So finding structures over the entire trace. And then we need to test whether our model has any relation with reality. I have this nice structure. And so the test we do is structure splitting and array regrouping. So source level data, we have many programs that operates on objects and they have many attributes. In Fortran, we use array allocation. In C, we use structure allocation, but neither is sensitive to the access pattern. And so array regrouping try to group things that are accessed together. Structure splitting, pioneered by Tricia's 1999 PODI paper, trying to split structures so that the ones that are used together are grouped together. And with reuse signature, we can reduce this problem to the comparison between reuse signatures of different arrays of attributes. In this example, I have a tree node structure. These are 3 of the attributes in the tree node, and I can measure the reuse signatures. And here, I drop the short distance reuses, which accounts for over 90% of accesses. But only the longer ones are important when we thinking about cache misses. And then I change the y-axis to be absolute number of references, not percentages. It's hard to resist using statistical clustering. Whenever we have vectors, we want to find their relations. And so k-means, x-means are the most popular statistical techniques. The problem with general clustering is that it's relative. So if x, y, z are the reuse signatures of 3 structure attributes, and showing by this example that the grouping decision of x and y is actually determined by the position of z, not by the position of x and y. So that was a good result in the sense that at the beginning we had this fear that people who works on general clustering may know more about programs than we do. That's a frightening thought. But we want to really measure the closeness based on the reuse signature of the attributes involved. So one test we tried is to require that the difference between 2 reuse signatures to be at most k% of the average reuse distance. And this didn't work well either. And Ital came up with the idea that we had this theoretical definition. We went through all these troubles to have the linked path defined and have the proof that with this linked path k, we can have unique partition of program data. So why don't we check for this link length k. So the difference in reuse distance must be within the link length k. So that's the absolute bound in the difference. And not until we started doing experiments did I realize that how elusive this notion of best data layout was. For a structure splitting, there are exponential number of choices. Swim is the one that has most number of attributes, 14 arrays. There are 6 million possible layouts. So finding the best one seems to be impossible. And also there are different machines, different compilers, and factoring their effect. And also the theoretical result, right? Optimal data layout is unreachable. Not only it's an NP-hard problem, but it belongs to this small group of problems that do not have good approximation.
So I actually cited that paper too, but after rereading the paper a couple of times, I decided that that result doesn't apply to kind of the stuff we're talking about, because it makes certain assumptions and abstractions that don't apply. So it's not like it's an easy problem, but I don't believe that that result tells us that, you know, it's in this class where you can't approximate efficiently with it. So you can talk about it offline.
And let's test. 2 machines. We tried SGI and SUM, but they're much slower than these two. So I won't show them. And let's just pick 3 programs. We tested 9 programs. Original execution time, we see that IBM machine, on average, is about 50% faster than Intel machine, except for this TSP, which is travel salesman problem. So it doesn't matter what the publicity they do. It's not fully optimized for a mobile user. Let's try X-means clustering. And I'm using the same data layout for these 3 programs, just using them on 2 different machines. So we see that the X-means layout for Swim is faster than the original layout for the same program on the Intel machine, but on the IBM machine it's actually slower than the original data layout. And then we use k% difference as the criteria. If we say k is 1%, we see the same phenomenon with Swim. The same data layout is faster than the original one on PC, but slower IBM. And if we look at the TSP, we see the same sort of inconsistency between X-means and 1% layout. So 1% layout is slower than X-means on Intel machine, but faster on IBM machine. And we don't know what's the best parameter here. Let's try 0.1%, which looks very good for Tomcat V and TSP. I get best times on both machines. However, for Swim, the 0.1% layout is actually slower than the original data layout, slower than GCC. So that's hardly a compliment. And so doing these experiments, it's very baffling because it seems to be throwing dots randomly, and there is no consistent relation between these different data layouts until we look at the k distance analysis. So really using the link length k, check for this absolute difference. So 1k is 256. And suddenly, we see that we have the data layout that's consistently better than other layouts on both machines, and also actually on other machines as well. Yeah.
So how did you generate these numbers? Because it seemed to me there would be enough variation in multiple runs that you can't really distinguish 40.4 from 40.3, right?
What we did is 5 runs and get the fastest time. And in fact, we did more than 5 runs. In the final paper, we have more programs, so we did more runs. And Ito asked me, which one do we take? I said the lowest of all the runs. Yes. We take the fastest possible time as the number here.
So what's the reason the Pentium is so much slower than the Power 4?
Power 4 has much higher bandwidth, and also the compiler.
So it's memory limited, the Pentium 4. So there's more opportunity to prove it because you offload the memory bus basically.
And the IBM compiler is also better.
TSP is much better, right? Yeah. So what's the explanation from that?
I think it's not as floating point intensive as the other. So if you look at Zoom and Tomcat,
we have a few other integer programs from the Olden benchmark. So those programs, IBM is also faster.
Then why is TSP Intel so much better on?
TSP, okay. But we actually look into this. TSP has this division operation. When calculating the distance between two cities, always do this division square root. Intel probably has a hardware implementation of division, but IBM maybe it's macro coding. But that may be the reason. And we see that the more attributes a program have, the larger the improvements we get from k-distance analysis. Swim is really the prime example, the best result, partly because it has the most arrays in the program. And there is a reason that it's difficult to do better than the original data layout. This is highly tuned by the IBM compiler group because Swim is part of benchmarks which used to show the performance of IBM machines. But among 6 million data layouts, without a good model, with a good model, we can actually do much better. And what's really remarkable is the consistency of the k-distance analysis against 8 methods on 9 programs on 2 machines. It wins or ties 97% of cases and never loses by more than 1% or a small fraction of seconds. So if we look at the IBM result for Tomcat V, we see that k-distance is actually slower than x-means by 0.1 second. However, the same 2 data layouts, on the Intel machine, the k-distance analysis is faster by 1.3 seconds. So on average, k-distance layout never loses to any other layout.
So did you do the experiment for like at least one of the cases where you kind of evaluated all possible layouts, all 6 million or whatever they are, and get an idea of how close to optimal you are? Or?
6 million is
6 million into 20 seconds, right? Just a couple of days of computer time.
Right. That'll be a good thing to do. Although, given this consistent this is statistically significant.
Right. I just want to know, like, is it
whether we're really good? Yeah.
Or there's still some room to go?
But then, to really test, we also need to give different input sizes.
Sure.
So far, we haven't found a faster data layout. We actually did other things later.
So what was this, the process? You used the train input to figure out the radius distances and then use your model to predict the test, and then you
right.
get the splitting based on the predicted thing for the test. Is the layout tuned for a particular input, or is it tuned for?
So this one, we just take the train input and then get the structure. This is the hierarchical structure of Swim. So based on the affinity, based on this link length K, is a hierarchy, and we draw it as a dendrogram. And K equal to 256 means just cut along 2 to the 8th, this line, and the subtrees are different, will be in different structures. And we tried different inputs and compared the structure of the dendrogram for a few programs, and they seem to be the same. This upper part changes with the input size. The lower parts do not change. This analysis can sort of get information from multiple runs. And when Vital gave the presentation at PODI, somebody asked if you have multiple training runs, what do you do? And in fact, it's quite simple. This is based on reuse signature. You can just collect all this information together. It's faster.
But does it get better? Did you try that?
Based on different runs, what we saw, the structure is very similar. But we don't have an example that the splitting choice would change as a result of data input. And reference affinity is what I consider may qualify as a contribution, as a scientific contribution. It's a theoretical model that has no equivalent counterparts in the traditional models, and it's the first general hierarchical model of data locality. And the empirical evidence is just overwhelming that the model captures something in these complex programs. We saw that the link length was critical. The moment we added that constraint, and we suddenly see regularity in the result of the optimization. And also this part is beyond much. I didn't expect that reference affinity, the k-distance analysis, can give us the best data layout. But of the test done, the k-distance results seem to be better than anything else we have tried.
So how do you make the claim it approximates optimum if you don't know optimum?
And that is not easy. We haven't been able to get anything better than this.
So it seems.
Seems.
That's a pretty good hedge.
And IBM compiler group was so impressed. They asked for a student to work there, and Shipeng went there, designed compiler algorithm for affinity analysis, for sort of similar to k-distance analysis, and then found they're effective for floating point programs. Because the IBM people tell us that users do not do profiling, let alone the expensive type profiling we do. The matching reuse distance is pretty expensive. And it turns out for floating point programs, it can be approximated just looking at the program code. And that's a very encouraging result because the trace-based models turn out to be useful for compiler design.
Question. I just want to check my understanding of link length here before we move on. I understand on average that it's going to be better to have shorter link lengths than longer link lengths on average. But is it true that when you get unlucky, even very short link length, say a link length of 2, that can be enough if there's one hop from between your origin and your destination. That one hop can toss things out of the cache. If you're unlucky about how things are organized in the cache, you could lose arbitrarily much with even a short link length in individual cases if you get unlucky. Is that true or false? Is there something I'm misunderstanding there?
So if I have, say, A, B, C, 3 data elements, I say they have reference affinity k equal to 2. That means if A is accessed, then within reuse distance, within access of 2 distinct data elements, B or C will be accessed.
Right.
And so if I group them together in the same cache block, then once that cache block is loaded into cache, I know that it will use A, and then the same cache block will be reused.
But if something is reused in
Something is accessed between, you could knock up B, right?
Right.
Pathological case.
Right.
The mapping.
Yeah. So a short link length should reduce the chance that will be reliable.
Okay.
And then I'll quickly talk about program phases, basically a high-level view. It's the thesis work of my second student, Shipeng. I don't want to take his thunder away. And I want to make the point that sometimes we can predict the large granularity behavior even when the fine-grained behavior is not predictable. So we can be fairly sure that the average temperature of the winter is lower than the average temperature of summer. But predicting sort of the temperature, whether the temperature of a particular winter day is lower than the temperature of a particular summer day, is not as certain. And in phase analysis, in what we do, we try to capture this large coarse-grained behavior in something we call program behavior phases. A phase is a unit of predictable behavior. So the behavior may not be uniform within the phase instance, but it's predictable, or it's predictably unpredictable. And also the phases are marked by program points in that when the control flow reaches this point, the phase must start. And also different phases are either nested or disjoint. We cannot have partially overlapping phases. So this gives us active adaptation because when a phase marker is reached, now the phase must start from this condition. And also we know we can predict how much we can predict the behavior. And then nested phases give us different granularity of prediction. Program phases have variable lengths. So I want to show you the difference between variable length phases and fixed length phases. So that's a program. We did behavior analysis and find these variable length phases, and then go back to the program, mark the phase boundaries. And then when it takes a new input, it will self-forecasting its coming phases with different lengths. And so for the test input, variable length phase, there are 7 different phases and 5,200 instances of them. And to see whether their behavior repeats for the same phase, I use the cache simulation to characterize the behavior as the miss rate over 2 different size cache configurations. So I can draw them on a 2D plot. And each instance, based on their miss rate on these 2 different cache sizes, is a cross on this plot. But we're not seeing 5,250 crosses. We only see 7 crosses here. That's because instances of the same phase have exactly the same behavior, so they map to the same point in this picture. So that's because the instances of the same phase has the same behavior, we can predict them with high accuracy. So we can just, for each phase, profile the first instance and get the behavior and use that to predict the behavior of all other phases, all other instances. And with hardware support, a lot of studies done recently showing that we can use fixed length intervals and then find behavior patterns. For this particular execution, if I divide this into 10 million instruction intervals, then I have about 2,500 intervals. When I draw their behavior as dots on the same 2D plot, we see that the regular behavior that we see from variable length phases becomes sort of a random spread. So in this example, that shows that knowing the exact length of the phases is important to capture the regularity in behavior. I also want to say that intervals actually work fine if the program behavior is steady or is changed in the fine granularity. And this is our newest result. The GCC, this is matches with our expectation that the temporal behavior is actually not predictable. This shows the IPC, instruction per cycle, measurement using hardware counters on IBM. And do we see structures or regularities in this behavior? It's not clear. But using behavior-based program phase analysis, Shipeng found that the outermost phase corresponds to the compilation functions. And for the compilation of each function, there are 8 subphases. So we found 8 phase markers in this large program. The first analysis was done on the binary program, so we didn't even need the source code. And then once we run the program with the phase markers, so the left picture shows the same input, we see that it's actually compiling a lot of functions. And then each function has subphases. The phases are more visible when we look at the different input. 166, it compiles 2 really large functions in addition to small ones. So here we see that subphase markers really captures the behavior change in IPC.
So I have a question. So why do you feel so phase is a dynamic behavior, right?
Mm-hmm.
And here you're trying to capture it with static phase markers in some sense. So why do you think that they should be a correlation, or is there a correlation? Is that the right way of?
Right. First, we want to know the structure of the dynamic behavior, and next we want to have some control prediction for that behavior. So knowing statically which marker marks the beginning of a dynamic phase is useful information. Now, I guess your question is whether that's always possible.
Right, exactly. It would be possible in some sense. Like, you need some context or some other additional information.
May not be possible.
So how do you determine where the phases start? What mechanism for determining?
And so the previous analysis used signal processing techniques.
Based on the IPC?
Based on reuse distance.
Reuse distance, okay.
IPC, the range is pretty small. Reuse distance range from 0 to the size of program data.
Okay. And is it, when you talk about there's a certain static point at which a phase always begins.
Mm-hmm.
So that's but is it that whenever it hits that point, it always begins, or is it in a particular calling context?
For now, we always begin. So
Oh, really? Okay, and that works.
Mm-hmm. Right. So oftentimes, this is not the beginning of function call. But other techniques look at the calling tree and find the functions as possible unit phase, and then based on the context, to say whether it's an instance or not. At binary level analysis, every binary instruction is a possible phase marker. So our analysis actually does not depend on knowing the structure of the program.
So is it defined that the phase ends when the next phase begins? There's no dead space between phases? Is that right? Is that how you're defining it?
So if we know there are 7 instances of this phase, then we find sort of instructions that execute exactly 7 times in this trace. Mm-hmm. And there are each of them often. And then we can sort of match with where these 7 instances are. And then we can also try verify with other inputs. So eventually, if there is a sort of one that always coincides with the phase instance, then we can find it.
Okay.
And it's currently a hot topic, and many good people are looking into this problem. And I don't have time to look them in detail, but it's sort of in this case, we again trying to combine the program analysis with behavior profiling. And reuse distance has been used by many people to model locality and the memory performance. And in addition to what we have done in establishing patterns, reuse distance patterns across data and time, there is a third dimension, which is the reuse distance pattern across program code. So the group at Michigan Tech, using our tool, did a study and published in MSP last year. And then a group at Ghent University also looking into the same problem, and both found that the distance pattern across program code is predictable in most programs. And then a lot of recent uses of reuse distance in VM storage systems. Xiaodong Zhang's group at William Mary actually developed a better Linux VM manager based on reuse distance. The basic concept is actually very simple. The LRU look at the last access time to determine what to keep in cache. Their new scheme look at the last reuse distance to make that determination. So in that, if this page had a long distance reuse last time, then don't keep this in cache. So page make it more likely to be paged out. And there are different studies on behavior correlation across different inputs. And distance is one of the models of locality. Trisha and I are doing a tutorial on 4 models of locality, and the next one is going to be at PAC 2005. And previously, I looked at the optimization of scientific applications, and some of the results now have found their way into the Intel compiler, and also serve as basis for a lot of recent studies. And finally, I want to show you where we work and when we work. This is Twilight.
There's no snow.
That's where we work. That's when we work. And to summarize, really, we looked into this approach that combines compiler analysis and behavior profiling. The goal really is to target large-scale behavior. And we defined and verified several models that give us structured representation of the dynamic behavior. And then through the process, through empirical studies, we also found interesting emergent behavior from complex programs. And just showing you the pictures again, we found that whole program localities actually can be modeled for many programs, and also that reference affinity gives us a hierarchical structure of the locality relation among data, and finally their regularity even in very dynamic programs, the regular phase behavior in dynamic programs. And finally, I didn't do all the work. I want to acknowledge my students, collaborators, and the funding agencies. So when I tell my program manager at DOE about this trip, I emphasize that my last slide acknowledge the support of DOE.
Question? So you talked about uses of your whole program locality model and reference affinity.
Mm-hmm.
We didn't talk much about uses of phase model. So what are your thoughts on that?
Right. Many people ask.
Paper. You have to go to MSP.
That's why I want the advanced system.
Thanks, but now people sort of start to get tired of papers on phase analysis. and they'll say, what's your killer application? So MSP paper is our sort of the best we have as what the information can be useful.
So I'm curious about the spaces that you detect. How, if you find them after the fact, how hard would they have been to put in by the programmer into the text at the source level?
Mm-hmm. If the programmer writes the entire code, it wouldn't be hard.
Yeah, I mean, I've been an advocate of, giving programmers the ability. I mean, I think we do it here now anyway. It turns out in there's a lot of reasons why you want to insert into programs sort of event markers that say something is about to begin or something's about to end, and because you can, there are mechanisms in Windows where you can extract out these event streams and then visualize them. So you can sort of ask questions like, how long did it take between these two markers, or how many page faults happened, and things like that. So at some level, these things are already in the code. It's kind of a question of how hard is it to get it right, especially when you count on these spaces to do optimizations.
But one advantage of doing this automatically, not by the programmer, is that actually the subphases is more than 8. In the sense that over a short period of time, there are many markers that mark the same phase. And we just pick one here.
Okay.
So at the logical level, programmer may see these are different steps of the compilation. But when we look at the resource usage, not all steps corresponds to significant phases in the program. So that would be one reason to use automatic analysis. But automatic analysis is have a clear picture of the resource usage that programmer does not have.
But that could really change from architecture to architecture too, right?
Right, so having the automatic analysis help.
You want to do it by hand.
And the programmer specify all possible steps. Then certainly will make the analysis easier than the automatic will just pick. But then requiring the programmer to pick all the possible steps may be too much labor.
Well, I think this is another example where things at the language level and things sort of above the language level, which are sort of the, I don't know, kind of just higher level specifications of what's going on, really kind of converge. I mean, there's no, if somebody's written code where it says, this is where we begin the, something, and this is where we end the something, and their library calls to some event routine that, is a logging program that may or may not turn on. There's no reason to ignore that information. But if the compiler doesn't see that as something special, it's just going to see it as another call, and it's not going to understand that might be the beginning of a phase. I guess I think there is information in programs already that's has semantic or some kind of value here that is being ignored. So I think partly I think it would be very useful to do some of your analysis on some of the programs that that are Microsoft types of programs. I mean,
I was about to talk to you about that.
Because you can get a lot of data.
This morning, Trisha is phase analysis for C# programs.
Yeah, or Office. I mean, I was going to say the heuristics thing too. I mean, it'd be interesting to look at what kind of pictures you get for Word, Word or Excel.
Yeah, for phase analysis, we're moving into interactive ones. So if this PDF reader reads 10 pages, can we capture these phases?
It'd be a bit hard in case of interactive. I mean, what kind of patterns can one think of in advance in terms of interactive application?
Right. Also depends on what we want to capture.
All right. Thanks a lot.
I can thank each of you individually for coming.
And the millions of people watching online.